So Q is asking us if a rectangular playground is being built next to a school building, which will form one of the longer sides of the playground, and the school has 80 meters of fencing available to enclose the remaining 3 sides of the playground. What are the dimensions that will maximize the area of the playground? What is the maximum area? So we are looking for the area here. We're looking to maximize this value, which is the width times the length. So let's write down what we're trying to maximize in terms of width and length. There we go. And we also know we only have 80 meters of fencing. We're going to want to use all of it. And we're going to have 2 widths and a length result from putting it in a rectangular shape. We don't have to worry about this side because this is the side of the school building. So we don't have to use any fencing for that side. So 2 widths plus a length is going to equal our remaining perimeter, which is the length of our fence, which is 80. So 80 is equal to 2 widths and a length. Let's bring this over here and let's start rearranging this equation, because what we're going to want to do is define an area equation that depends only on one variable. Right now it depends on 2, and that's not very useful to us, except plugging in and trying different values of W and L that both add up to 80. But instinctively, you have to realize that if W is 0, L is 80. If L is 0, then W is, because of this equation, that W will be 40, because 2 W's is equal to 80. So we should be able to set this equation in terms of only one of these variables, and we can choose W or we could choose L. I'm going to choose L because we have a length here as a single variable, and it's nicer to think about. So I'm going to rearrange this in terms of W so that we can change what W is. I'm going to get W alone. I'm going to rearrange in terms of W so that we can replace W with respect to L. So this is how this is going to work. I'm going to subtract, divide by 2. So I'm going to get 40 and 1/2 L. And then I'm going to subtract 1/2 L to get W is equal to 40 minus 1/2 L. Let's do that now. W is equal to 40 minus 1/2 of L. You didn't follow along with that? Just try rearranging it, pen and paper, and you'll find that this is correct. When we plug this into W, we get a new area equation. I'm going to edit this equation. And I'm going to put length on the left. And then I'm going to replace W with 40 minus 1/2 of length. And what we find is this new equation. Oh, not equal to, minus. There we go. That's better. And when we factor this equation, when we expand this equation, we're going to get a quadratic equation that's going to describe an inverted parabola. What I mean by that is our first term in our quadratic equation is going to be L times negative 1/2 L, which is negative 1/2 L squared. And then we're going to have a positive term plus 40 L, which is this multiplication here. So I'm just expanding it out, and I find that area is equal to negative 1/2 L squared plus 40 L. So here is our new area equation. And I kept our old one on the board because it will be useful. Let's set up some axes and talk about what this looks like. Because the next thing you have to do is form an intuition of what the highest point is, what the maximum value of area is. And once you find this equation and you put it in a graphing calculator, you think about what the graph must look like. This is a negative coefficient on an x squared term or an L squared term, which means it's going to be a parabola, because that's what an x squared looks like. It's going to be a parabola, but it's going to be an inverted parabola. It's going to have its top be the so-called bottom of this parabola. Oh, I'm still drawing. It's going to have its top be the so-called bottom of this parabola. So it's going to look something like this. That is a line. Something like that. Pardon my very bad parabola. It's going to be an inverted parabola. And when we look at this inverted parabola, and we look at what happens when L is equal to different values, this parabola is going to have two zeros. It's going to cross the x-axis in two places. One where L is equal to 0, because then area must be 0. So we're going to put the left leg there, or the right leg, but intuitively, it's going to be the left leg. You can't have a negative length. So it's going to be here. And then it's going to have another 0 here, where L is equal to something that makes this part of the area equation 0. And plugging in 80 here will make this 0, because 40 minus 1/2 of 80 is 40 minus 40 is 0. So we can know that this is 80 and that this is 0. And because a parabola like this is exactly symmetrical, we have this midline crossing the parabola at x is equal to 40. We plug L is equal to 40 back into our area equation of A is equal to the length, which is 40, times the width, which is going to be 1/2 of 40. So that's going to be 20. And we find that the area is equal to 800. That is the maximum area of the playground, and the dimensions of the playground are 20 by 40.